Excellent. Okay. So to review, because want to make sure everybody's with me on this. Making a silica aerogel via sol-gel process is often done using silica alkoxides. And so the two overall steps in this reaction would be hydrolysis to change the silica alkoxide into a hydroxide species, and then condensation reactions that link the hydroxide groups together by splitting out molecules of water, or link an alkoxy group with a hydroxyl group to split out an alcohol. And I will show those reactions again. The common silica alkoxides we use, and in fact the ones that were used for the monolithic silica aerogels you just saw, were TMOS or TIOS. And so you just saw some TMOS-based aerogels. So this is just a CH3 group on the end of this. TMOS by itself is a clear colorless liquid. And as was explained on Tuesday, we mix TMOS with methanol, a little bit of water, and ammonia as a catalyst. Hydrolysis reaction, we're looking at the top one here, the TMOS would react with water. The hydrolysis reaction is between the methoxy group that's here, the OCH3, and the water, splitting out a methyl OH, so that's methanol, and leaving a hydroxyl group on the silicon. Now, depending on how much water there is and how much time we permit, we could have 1, 2, 3, or 4 of these groups react to make hydroxyl groups. And so this is the initial step in making the gel. We then would do condensation reactions. And there are two general types of condensation reactions. Again, I'm going to focus on the one involving the TMOS-based species, just because those are the examples we just looked at. If 2 of the hydrolyzed TMOS molecules react together, we make the silicon-oxygen-silicon linker and split out a water molecule. If, on the other hand, a hydrolyzed TMOS reacts with an unhydrolyzed TMOS, we still get a silicon-oxygen-silicon bond, but in this case, we would split out methanol. And so the reactions will be happening, both of those reactions will be happening, and they'll be happening on the multiple branches of the various silica species until we make some small clusters of silica-containing particles, at which point we will have a colloidal solution, or the sol. As the sol particles continue to react with each other via condensation reactions, we make the gel. And so this takes a little bit of time, depending on how much catalyst is used. The typical recipes that we use under room conditions, gelation would occur within about an hour, maybe 2 hours, depending on the amount of catalyst that's used. But these aren't the only sources of silica that can be used for gels. It is a very common one. It was the focus of the first lecture and the review that I just did. But silica is also a major component of some industrial and agricultural waste products. And those include things like rice husks. So silica, SiO2, is going to be about 15 to 20% of that. Silicates and coal ash. It's also known as fly ash or flue ash. This is the ash that results from burning coal. Depending on the type of coal, could be 15 to 60% of it is made up of silicates. There are also a number of water-soluble silicate salts, which collectively are called water glass, and they are soluble in water, and they could also be employed. Now, the chemistry is going to be a little different for the different silica-containing species, but these are all silica species that are available. And certainly, there have been increasing efforts. You see a lot more work in the literature in demonstrating use of some of these sources, both because they're relatively inexpensive and also for sustainability reasons. If there are ways that we can use things that would otherwise be waste products to make an interesting and useful material, then that's certainly an advantage other than just disposing of the waste. Okay? It is, however, slightly more complicated to make them by those methods, as opposed to starting with, commercially available chemical silica alkoxides that you could purchase, right? So there's going to be significantly more processing, right? If you wanted to make aerogels out of rice husks, well, you're not going to use the whole rice husk because it's only 15 to 20% silica-based product. So there's going to have to be significant separation. Working with the silicate salts, for example, often involves doing an ion exchange, sort of separation methods as well. But there's increasing use in that. And so Professor Anderson also touched on this at the end of her presentation yesterday, that silica aerogels, carbon-based aerogels are the real industrially made ones. There are lots of other types of aerogels, and we are going to talk about some of them today. But the price of some of these aerogel products is relatively high, and it depends on the availability of materials. And again, she had this here. There are a number of different things that can be used that would otherwise be industrial waste products to make aerogels. And so there's increasing interest in using reusable or renewable sorts of sources for some of these things. So I want to talk a little bit more about silica-based aerogels, and then we're going to take a break and talk about other kinds of aerogels from different chemistries. So hybrid and doped aerogels do not have to be silica aerogels, but the examples I'm going to show in the next few minutes will be. So what we can do is mixed metal aerogels by using two different co-precursors. So instead of just using a silica co-precursor, if we used silica co-precursor and a titania precursor, or an alumina precursor, or a copper precursor, or some other species to make an aerogel that contains not just the silicates or silicon oxides, but also other things. We can do that by putting them in as a co-precursor. We can do that by making one type of gel, and then during the aging process, impregnate something else with it so that the reaction that continues involves a different chemical species. There's a significant amount of work that's been done in polymer reinforced aerogels, filling some of the spaces with polymers that yield strength. There are organic, inorganic hybrid aerogels, and then there's just what we call doped aerogels, where you just trap something in the gel while it's forming. And so I'm going to focus on some work by a couple of other groups. Smirnova's group, she's at Hamburg, for example, has done a fair amount of work with aerogels for drug delivery. And one way that one can do this is by taking the sol and before it gels, mixing in some active compound, a drug, so that when it gels, the drug species are simply physically trapped within the spaces in the gel. They're using supercritical CO2 drying to make an aerogel drug mixture and then pulling the drug out. Or they can do it a different way. They can make a silica-based aerogel, for example, which is very porous, and then they can add the drug in supercritical CO2. So dissolve the drug in supercritical CO2 and load it into an already prepared aerogel for subsequent delivery. One can trap things as large as proteins and nanoparticles, or as small as dye molecules within the matrix this way. And so you can take advantage. This would be a putting it in before it gels, putting it in after it gels, if there's a way to do it without pore collapse. There are lots of different interesting hybrid things that can be done. In the next couple slides, I'm going to focus on some work from Deborah Rollison's group at the U.S. Naval Research Laboratory. And this was published in 2000. It was just on, so it's a while ago, about silica aerogel composites. The basic idea is that if you can entrap some particles that are on a nanoscale, they might be larger or smaller than the colloids, that, the individual clusters that we had here in the aerogel, but they're not networking to each other. They're being trapped in this network. If you can get the solvent out of the pores without pore collapse, these are then going to be accessible to do interesting sorts of applications, right? It could be a catalysis application. It could be an energy or sensing related application. They will still be accessible to gas phase things. Under drying, under ambient conditions, it's going to collapse, and that may make whatever we've just put in fairly inaccessible to anything else. So the advantage of the aerogel here is the porosity. So they're looking at using the aerogel architecture and essentially decorating the aerogel architecture with some interesting functional groups. And so here, this just indicates some sort of nanoparticle. The paper that I took this from, they actually made a wide variety of silica aerogel composite materials. So they had plain silica aerogel, which is what we were just looking at, demonstration. They've put nanoparticles, colloidal nanoparticle solutions, platinum nanoparticles, gold nanoparticles, carbon black. Obviously, this is not a transparent aerogel. PMMA, polymethyl methacrylate, that's a very common polymer. Okay. Zeolite containing iron complexes and 2 different types of titania, just as a way of showing the different things that could happen. The overlaying it with the periodic table is simply to show the transparency of some of these. It doesn't align with what the chemical structures of these are, right? Carbon's over here, for example, right? Titanium's over here. So they haven't, they're not actually aligning the periodic table with the different things. And so again, here I'm just talking about what could they do. So how did they do this? Well, they did a very standard TMOS-based silica sol. They're using TMOS, the precursor that I showed you we used for those window samples, water, methanol with a catalyst. They then mixed that in with a sol that they had that contained what they're calling the modifier, the type of nanoparticle. They poured them together before this fully condensed, and then the individual particles here become entrapped. They allowed it to age. They're calling it washing. I would call it solvent, solvent exchanging. And then they did supercritical CO2. Subsequently, they annealed it, so they were heating it. We'll come back to that later in today's lecture. And they were able to show that by annealing it, by heat treating it, they were able to strengthen the network so that it was capable of being in contact with solvent again. Sometimes if you take an aerogel and you try to put it back in solvent, that's going to cause pore collapse. And so they were trying to make architectures that would survive that. Now, I should note something. Whether you could use a different extraction process for this, freeze drying or rapid supercritical extraction, is going to depend on the nanoparticle modifier, right? So if what you're trying to put in here, if these particles, for example, were proteins, the chances that you could do high temperature extraction are very small, right? Because the protein would denature and decompose. And so it's not so much that the chemistry would be the problem, it's that the temperature conditions would be a problem. Similarly, with freeze drying, it's going to depend on which solvent you have. And as Professor Anderson said yesterday, one of the issues with freeze drying is you can have some breakage of the structure during that. And again, it will, whether or not the particles that are being used can tolerate that will depend on what the particles are. So something like platinum or gold nanoparticles would be able to be used in a high temperature or a freeze drying situation without much difficulty. Okay. There are many different types of aerogels, and I'm not showing these. I'm showing 3 that we've made with some SEM images here. You can see some of the porous structure in these. Aerogels are actually very difficult to image with scanning electron microscopy because of their insulating ability. And because in scanning electron microscopy, you're sending electrons to the surface to do the imaging. If you have a conductor, those electrons can be sent to ground. If you do not have a conductor, you end up with the electrons becoming trapped at the surface. Subsequent electrons are then repelled by those electrons, and it's a problem known as charging that makes it difficult to image them. But you can see that we'd have different properties. These are all gels that we have made at Union, silica, titanium, and aluminum-based gels. But you can see the overall porous structure, nanostructure of the different materials in the SEM images. You'll note that the scale here is a 1 micrometer scale. These are a little, not much, but a little bit closer with the 200 nanometer scale. So this is, these are maybe twice the magnification of the others. So before the break, I'll talk about alkoxide-based approach to making alumina aerogels. So with the silica alkoxide, we had a silicon with 4 alkoxy groups. Aluminum is only going to make 3 bonds. And so we're going to have potentially 3 groups around that. This is an alkoxy group. We could just do an R like we did before, OR. Right? So if we can have a silicon alkoxide, we can have other sorts of metal alkoxides, and we can do a similar kind of chemistry. We can do hydrolysis, reaction with water, and that, if it happened in all 3 locations, would give us aluminum hydroxide. Right? With 3 hydroxides, it would split out some solvent. In this case, if we're counting 1, 2, 3 carbons, this is going to be a isopropanol released. Okay, and these can then condense by reacting with other groups of the same thing to make aluminum, oxygen, aluminum bonds. So I'm not going to show all of the chemistry. What I am going to show is this SEM image where you can actually see the cluster pattern. This is a 1 micron diameter, roughly individual pieces within the colloid, and you can see what is sometimes called, like a chain of pearls shape to this. So this is a very nice image that was taken by one of our students. The gel itself is not transparent, so this is not the sort of gel you would use for a window sort of application, but it is a nice monolithic gel. The chemistry involved here, though, is a little bit tricky in terms of temperatures for different steps and the process. And some of the precursors and thus the alcohols used don't smell very good. And might be more of a concern for release. And so this is more complicated, the individual steps. We can also make metal oxide aerogels with an epoxide-assisted approach. And this is going to be the most chemistry-intensive slide that we have. So I think what we'll do is we'll talk about this one, and then we'll take a break, and we'll come back and revisit it. So this is a non-alkoxide recipe. So what we're doing instead is we're going to start with some sort of metal salt. So we could start with an aluminum chloride salt or chromium nitrate. So when I'm showing this .6H2O, this means it's a hydrated salt. It means that in the solid phase, for every 1 aluminum ion and 3 chloride ions, there are 6 water molecules as part of the overall crystal structure. When you dissolve it in water, those waters just become part of the solution as a whole. This is chromium 3 nitrate, so there'd be 1 chromium 3 ion for every 3 nitrate ions, and when that crystallizes, you often have multiple water molecules. In this case, 9 water molecules could be there. This is an approach that Baumann and Gash and a number of other people at Lawrence Livermore National Laboratory in the US first published, and a couple of their papers are cited right here. The idea is that when your metal ion is in solution, what you really have is a complex between the metal ion and water molecules that are tightly bound to it in solution. So in this cartoon, we're showing a metal ion with 3 closely associated water molecules, instead of with some organic alkoxy groups chemically bonded to it. So a slightly different approach. If we put in an epoxide, so we're seeing here, this is propylene oxide. So this is a very constrained system. We have a carbon with 2 hydrogens here, carbon with 1 hydrogen and a methyl group here, and an oxygen here. This bond angle is very constrained. This is a highly reactive species. And if you have a metal hydrate, so the hydrated metal just means a metal ion with some tightly associated waters. This can scavenge a proton or an H+ from one of the metal hydrates, leaving us with a metal OH bond here, and then this has the proton over here. And these can then start to condense through condensation reactions to make metal oxides. So using something like this, we have an aluminum hydroxide species that can condense to form aluminum oxide. If we did the same thing, if this was an aluminum 3 ion here, we would make an aluminum to oxygen to hydrogen connection that could then link together to make aluminum oxide. So this is a different approach to making a similar type of chemical species, the aluminum oxide. Now, we've used our rapid supercritical extraction method to make a variety of catalytic aerogels, some of which we've involved the chemistry I just showed you. So for example, for nickel, aluminum, cobalt, aluminum, and copper, aluminum aerogels, which have different color based on the transition metals, the nickel, cobalt, and copper. These were all made using the epoxide-assisted approach. We've also made vanadium silica and titanium silica aerogels using the silica chemistry that we talked about, more of an alkoxide-based approach. We've published a number of papers in this area, and we're going to talk about some of the ways that we make mixed metal aerogels after the break. But I think this would be a good place to stop before the break. So why don't we meet back again at 10 minutes after 11? Sound good? Yes? Okay. That's what we'll do. So, okay, Saeed and Pier Giovanni, are you back from the break?
Yes.
Okay, great. And so I'm going to start again, and I will ask you whether you can see the screen. Can you see the screen still?
Yes.
Excellent. Okay. And so I'm going to talk a little bit about some of the approaches that we take to make the mixed metal aerogels. And one approach, which we refer to as an impregnation approach, is to make one type of aerogel, and then during the aging process, introduce the other species that contains the other metal we're interested in. And so I promised that I would go through the chemistry again, which I will. In the example shown here, we first make an alumina aerogel using the epoxide-assisted approach, stirring propylene oxide into a solution of aluminum chloride in ethanol, and we make an alumina sol gel. So I'm going to back up. Maybe. So this would be, again, if I had an aluminum salt in solution, the aluminum ion would have some water molecules tightly associated with it. This is particularly true for species like aluminum, which has a +3 charge, chromium-3, which has a +3 charge. The charge densities of these cations, positive ions, is very high because they are multiply charged and therefore very small. Because they've lost, if you think of an aluminum, it's lost 3 electrons compared to an aluminum atom. And so you have the same number of protons, but 3 fewer electrons. The remaining electrons can be held in much more tightly. And that means you have a small, highly charged species, and that's going to attract the water molecules, the negative end of the water molecules, partially negative end, where the oxygens are. So the waters can be reasonably tightly bound. You can think of it as a complex between the aluminum. Okay, and so we have these water molecules. We have propylene oxide, which scavenges some of the protons, the H pluses, leaving us with, in this case, an aluminum oxygen hydrogen link here, which can then form condensation reactions so that we get an aluminum to oxygen bond. And when we do that here, when we stir propylene oxide into a solution of the salt, typically gelation occurs. So hydrolysis and condensation occurs within 3 minutes or so to make a gel. Now, the alumina gel is clear and colorless. We typically would then let the gel age for about a day, and then we break it into pieces. I'll get into that in a minute. And we get rid of any excess solvent, and then we do a series of solvent exchanges. And in the first solvent exchange, we add the other salt we're interested in. So in this example, what we're doing is we're doing an impregnation with nickel. We're trying to make a nickel alumina aerogel. And so in the first solvent exchange, we put nickel nitrate salt, which was probably hydrated, but I'm shortening it here. So a nickel nitrate salt in ethanol, in absolute ethanol, and we use that as the first solvent exchange. So then the nickel solution in ethanol replaces the ethanol that was in the pores in the first place. We then do 2 subsequent solvent exchanges with pure ethanol. And when we do those solvent exchanges, most of the nickel stays in the gel because during this exchange, the nickel species has reacted through condensation reactions with the exterior and even the interior pores. I'm saying so with the places that were still available for reaction. So where aging would have still been occurring, we're now introducing another chemical species. What we end up with are pieces of nickel alumina aerogel that we can process. Now, I said I'd circle back to breaking it into pieces. For the application that we were making these materials for is a catalytic application. We don't need, although the RSCE process that we invented does allow us to make monolithic aerogels, we don't need single piece aerogels for this application. And consequently, if we are going to do a solvent exchange on a monolithic piece, because solvent exchange requires the solvents to diffuse in and out of the material. If we have one big material, one big piece, it's going to take longer for the diffusion to occur than if we break it into smaller pieces. And since in this particular case, in our application, we were going to break it into pieces at the end anyway, we break it into pieces so that the solvent exchanges occur more rapidly. So we have individual monolithic small pieces that we can do exchanges on more quickly. And so then once we process that to make aerogels, we end up with nickel alumina aerogels. So the aerogel contains both the aluminum oxide and nickel oxide species. We can also take a different approach, and that is, instead of starting with one salt and making a gel, we start with a mixture of salts. So in this case, we started with an aluminum salt and a cerium salt, and we dissolved them together in the solvent. We typically use ethanol, and added propylene oxide. And a gel forms that contains both the cerium oxide, which is known as ceria, and the aluminum oxide, which is known as alumina gel. So we take that wet gel, and again, we break it into pieces to facilitate solvent exchange, and do 3 solvent exchanges with ethanol, and then put the pieces of the gel into a mold and do our rapid supercritical extraction. Now you might be saying to yourself, this doesn't seem as rapid anymore. One of the big advantages of our method for making silica monolithic aerogels is that we can mix the chemicals together, pour them in the mold, set the hot press parameters, walk away and come back in a few hours, and we have intact aerogel monoliths. So the advantage of that Professor Anderson articulated yesterday over some of the other methods is the fact that it's rapid. And our processing here is still rapid. The rapid supercritical extraction in the hydraulic hot press is in fact going to take only a few hours, typically 4 or 5 hours for this particular case, because we didn't have to do gelation in the mold. It's already gelled. But we now have done 3 solvent exchanges, each taking 24 hours. Or in the previous case, we might have aged and then done 3 more solvent exchanges. So it's this is no longer as fast, and one might be wondering, why are we doing these solvent exchanges when we did not do solvent exchanges previously? And Professor Anderson emphasized that for supercritical CO2 extraction, it's necessary to do solvent exchanges in order to first get a more nonpolar solvent into the gel and then get liquid CO2 into the gel prior to doing the extraction. Here, the issue is not so much what the solvent was, it's what the epoxide was and some byproducts of the initial reaction. And so we undertook a study associated with our alumina epoxide-based approach, where we looked at how much was still left. So taking the solvent from the solvent exchange and analyzing it by gas chromatography, mass spectrometry, to look at what was present in the solvent after the solvent exchanges. And if we look here, we have 2 things. We have the peak area in the GC, which means the amount, essentially. It's proportional to concentration. And we have the surface area of the aerogels that we subsequently made. And what we see is if we don't do any solvent exchanges, we can, in fact, make aerogel, right? The process still works. But the aerogels that we make, in this case, had a surface area less than 500 meters squared per gram, which is still pretty high surface area, right? But when we looked at the GCMS, we saw that we still had quite a bit of propylene oxide remaining in there. If we do 1 solvent exchange or 2 solvent exchanges, let's go to 2 solvent exchanges. Now we've decreased the amount of propylene oxide in the solvent after the solvent exchange, what was left over, significantly, and our surface area is up slightly above 600 meters squared per gram. And if we do 3 or 4 or 5 or 6 solvent exchanges, we get to the point where we are not getting significantly better aerogel, but it's just taking more time. And so typically we do 3 solvent exchanges. We're doing it to get rid of the propylene oxide and also some of the other byproducts of the reaction and some of the impurities that were present in the ethanol and the salts that we were using for the synthesis. Our exchanges are with absolute ethanol, which is 100% ethanol. And another advantage is we can then, we only have to get above the supercritical point for ethanol as opposed to an ethanol mixture. And so this is the reason that we do the solvent exchanges, but it does mean that we lose some of our advantage for our method being significantly rapid. And another thing I want to talk about that's related to this is calcination, because in some of the, for some reason cannot move this window. Okay, I'm sorry, I had to just close that so that I could move the window. There we go. There's making aerogels and then there's using the aerogels. And sometimes after initially making the aerogels, we want to have them undergo some more thermal or chemical treatment. And so I want to talk a little bit about that because there's chemistry beyond that as well. And a term that you will likely see in the scientific literature and particularly in the aerogel literature is calcination. And calcination is what we would call a catch-all term. It actually covers a bunch of things. It refers to thermal treatment of a solid sample. And it's often performed in a particular environment. So it might be performed in the absence of oxygen, or it would be specified calcination under ambient conditions in the air, or calcination in a helium environment or something like that. You're heating the sample to cause some transformations to the sample. And those transformations could be one or more of a number of different things. And so when you first read the definition of calcination, it doesn't make a lot of sense. It's because a number of different things can happen when you heat a sample. Now, we're not heating it to melting. We're not trying to change its phase that way. We're looking to start with a solid sample and end with a solid sample, but the solid sample that we end with is different. So several possible things could happen. You could have desolvation. So if as part of your solid there was adsorbed water or adsorbed ethanol or whatever the solvent was, heating, thermally treating the solid sample will evaporate the solvent. Okay. You could, if there is an oxidant such as oxygen present, right? So if you're doing this in air, oxidation reactions could occur. You could also have within the chemical mixture of the material, you could have things that could also undergo oxidation reduction reactions. The question is what's in the atmosphere surrounding the sample and what's in the sample itself. So you could have some oxidation reduction chemistry happening. We could have thermal decomposition happening. This calcination is something that is done with ores, with metal ores. And this kind of approach to altering materials has been known for centuries, right? If you take an ore and you heat it, you could take a rock that was a carbonate-based rock and you could drive carbon dioxide off of it, leading to having an oxide instead of a carbonate. You could heat it more and you could end up with a pure metal rather than an oxide. And so thermal decomposition reactions can occur. And there can also be solid phase transformations. So in the simplest phase diagrams that we show for chemical species, we show solid, liquid, and gas or vapor, depends on your discipline, what you would call that. And you might see a supercritical fluid. But for very many species, there's actually more than one solid phase. There are different orientations that the atoms or ions that make up the solid could take with respect to each other that give different properties to the resulting material. And so you could have phase transformations, again, within the solid phase. I'm not talking about melting. So a number of different things that could happen during calcination. And this becomes important when we're thinking about using aerogels for different applications, because sometimes you make a gel and you want to make the gel have better catalytic activity, or you want to make the gel have increased strength. So we saw one example of this in the first part of the lecture, where I was showing the work from Deborah Rollison's group at the Naval Research Laboratory in the US, where they did some annealing. They heated it to strengthen the network so that it could tolerate being put in solvent without having pore collapse. Going to be other examples in the next examples that I show. And so I also want to talk about order in aerogels. And just to remind you, you probably know these terms already, but crystalline solids have a highly regular pattern of arrangement of the particles. So if it's an ionic compound, a salt, it would be a highly regular pattern of arrangement of the ions in the salt. So if you had sodium chloride or table salt, the sodiums are arrayed in particular ways compared to the chlorides. But you can also have sugar, right? Table sugar is a crystalline material. The sugar molecules are in a particular pattern relative to each other. And you can have crystalline atomic samples as well. Amorphous is the opposite of crystalline. Amorphous solids have an irregular arrangement of particles. And a typical example of an amorphous solid would be glass. So glass is made of silica, but it's not crystalline silica. The silica species within the glass are not arranged in a highly regular pattern. On the other hand, if you had the mineral known as quartz, which is also silica, that's a crystalline species of silica. So the silicon-oxygen-silicon bonds are going to be in very regular orientation relative to each other throughout the material. And in general, because of the way that we make them through the sol-gel process, aerogel materials are amorphous. They have formed in a non-crystalline way. There's an interlocking three-dimensional array of connections, but they are not highly regular. But aerogels can contain microcrystalline components. And this can happen really in a couple of different ways, and two of them are shown here. If we added crystalline solids, if we doped the sample, right, we're trying to make a composite material that contains some little crystals, and we've added them to be trapped within the matrix, that's one way we could end up with microcrystalline components. But crystalline species could also be formed during processing. And those crystalline species might be important to the properties and the uses of the material. So I'm going to show a couple of examples from our lab, and then I'm going to show some other chemistry beyond our lab. So ceria alumina and ceria silica aerogels, we did some work in a couple of years ago. I showed, I believe, the cerium aluminum, how we made those as an example of an impregnation approach. And so you can see our as prepared material looks like this. We also made ceria silica by impregnation and by the co-precursor method. And you'll notice that they're all a little bit different from each other. These are all pieces. And then after we heat treat them, they look different. Right? There have been some either structural changes, sometimes we see color changes that occur. We are working fairly frequently with some transition metals, and depending on the orientation of atoms around the transition metals, we can see color changes. So if we look at these materials, we can actually see what kinds of properties might have changed as we changed them, as we calcined the material. So for example, with the ceria alumina sample, we had a particular density. These are nice low density aerogels as prepared. After we calcined, they were a little bit more dense. It was more dramatic for the cerium silica sample. We also see, sometimes we see differences in the surface area. So after calcination here, for example, the cerium silica aerogel became more dense, and interestingly, also has higher surface area. Right? Sometimes we see a lower surface area because it depends what changes occurred. Right? Did the changes that occur cause structural changes that result in more surface being exposed or less surface being exposed. And so that can be really quite complicated to try to figure some of these things out. X-ray diffraction can be used to look at crystalline species. And so an as-prepared ceria alumina aerogel, this is an XRD. Notice how noisy this is? This is in part because this material is predominantly amorphous. And so we see only very small peaks from crystalline components. But after calcination, we see the signal-to-noise ratio is much improved. That's not because there's less noise, it's because there's more signal, right? So we have made some crystalline species that involve cerium-4. And the cerium-4, it is likely a cerium-4 oxide. We also see some crystalline components associated with particular phases of alumina. One of the solid phases of alumina is known as boehmite, one is known as gamma alumina, and we see evidence that there are some small structural changes occurring. Again, the material is still mostly amorphous, but we are seeing particular crystalline components, and we do see differences. So this is after calcination at 800 degrees C for 1 day. Then there's the copper ones. So these are copper alumina aerogels that are heat treated. So these are all the same type of copper alumina aerogel initially, but we heat treated to 100, 200, 300, 400, 500, 600, 700, 800 degrees C. And what we are seeing is significant changes. Now, some of these changes have to do with what we call the ligand structure, which is sometimes pronounced ligand structure, the tightly bound chemical species around small, highly charged cations. And so we may just be seeing some changes at the lower temperatures due to desolvation as water molecules and ethanol molecules are pulled away from the copper. We may see a change in color, but we also see evidence in the XRD that we're actually having changes in chemical species that following initial fabrication, we tend to have the copper either in a copper 0, that is the metallic, or copper 1 state, but by the time we've done a lot of heat treatment, the vast majority of the copper seems to be in the copper 2 ion state. And we've published this work as well. In some more recent work with chromia alumina aerogels, as prepared are amorphous. And here, this is with a newer XRD instrument, but you can see as prepared is at the bottom. And for some reason, the temperatures are not showing through here, but this is as prepared at the bottom. This is an amorphous material. We are not seeing evidence of peaks. We're not seeing evidence of microcrystalline peaks. And then we heat it to 200 degrees.
Do you know what XRD is?
X-ray,
I was going to say, what do you know?
All right, so X-ray diffraction, thank you. So Professor Anderson's making me explain something. X-ray diffraction is looking at the diffraction patterns off of crystals. So if you send X-rays in a collimated parallel beam toward a sample that contains crystals, the X-rays will diffract off of the crystal in a particular way, and we'll get a series of constructive and destructive patterns. So if we measure as a function of angle, we will see areas of constructive and destructive interference, leading us for the constructive interference to peaks for crystalline species. If you have an amorphous species, it's going to just be destructive overall, and you will not see peaks. And so this bottom trace basically tells us that as we prepared chromia alumina aerogels, it was an amorphous material. And then, did that make more sense?
Yes.
Okay, sorry.
Explain how the peaks are related.
I will. And then we heat it to 200 degrees C, and it is still amorphous. And we heat it to 400 degrees C, and we still have an amorphous. And we heat it to 600 degrees C, and we see crystals that give these peaks. And these peaks all match to a particular chromium oxide chemical structure. And we heat to 800 and the peaks are still there. So somewhere between 400 and 600, something happened. And we made a crystalline chromium oxide species. And if we then do scanning electron microscopy imaging, we can in fact see these individual crystalline things that have happened. So we had an amorphous species where the aluminum oxide and chromium oxide were all dispersed. And as we heated the chromium oxide species, things basically moved within the solid to make these. And you can see they're beautiful, they're thin, flat crystals. They have sort of a hexagonal, very nice hexagonal shape. This is a 2 micrometer scale, so these are a little bit less than 1 micrometer across, and they're significantly thinner than that. We have these little plates. Sometimes we see them clustered together. They almost look like flowers. This is a very different structure. I'm not showing the SEM image before heat treatment, but it just looked like aerogel, sort of fluffy looking. We didn't have these. These are clearly crystals. We can do what's called X-ray EDX, which is energy dispersive X-ray spectroscopy with the SEM to look at particular signatures for different elements. And we can see that the signal for chromium and the signal for oxygen is high in these places where we have crystals. So that's completely consistent with what we are seeing here from the XRD. So what has happened upon heat treatment, again, somewhere between 400 and 600 degrees C, is that we have started to form these crystals that then seem to be very stable upon higher heating. So significant changes can happen, and sometimes this is intentional and sometimes it's unintentional. So it depends on the application. In the work that we're doing with catalytic aerogels for automotive pollution mitigation, we need to have materials that could operate at a high temperature because this would be something that could potentially be used in the automotive exhaust stream of an automobile or something that has an internal combustion engine. And it's okay if a transformation occurs and then is subsequently stable if the material still operates, has the properties that you need. It's not okay if we're going to see an overall decomposition. And so we do see that we form crystals, and that seems to be stable. These materials are catalytically active as well. And so an obvious question is are the crystals important in the catalytic activity? And that is beyond the scope of what we're talking about today. And frankly, it's an area that we're still working on. So this is a different type of approach. And now I want to spend the rest of today's class talking about carbon-based aerogels because they're the other really important type of aerogels. We in the aerogel lab at Union College have not worked significantly with carbon-based aerogels. Most of the approaches to making carbon-based aerogels are not compatible with doing high temperature supercritical extraction. And that's just because to make carbon-based aerogels, one would typically be using organic starting materials, and organic starting materials tend to decompose when heated to very high temperatures. And in order to do the rapid supercritical extraction, we have to take the aerogel in the contained mold above the critical point of the solvent that's in the pores. The other reason we haven't done it is because I don't want to work with formaldehyde and the method that we're using and run the risk of having formaldehyde in the exhaust stream. Typical traditional way of making carbon-based aerogels is using what's called the resorcinol formaldehyde, or RF. This does not mean radio frequency. It means resorcinol formaldehyde aerogels. You start with resorcinol, which is this small organic species, 1,3-dihydroxybenzene, and we start with formaldehyde. And the reaction that occurs links these species together, making polymer chains. So you can see that they repeat And these, dot, 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 right? It's going off. This is a chain where it can go off in different directions. So we have long polymer chains. This is an RF polymer chain. And so each of these are chains, right? Great big long polymer chains. How do we get an aerogel out of that? Well, again, now we're just blowing it up. And now we're going to use this squiggle here, this little, to mean the polymer chain. Okay? And so polymer chains are formed. And then those polymer chains start reacting, cross-linking between the different chains to make nanoparticle clusters. Okay, so this is our sol. And after about a week, they agglomerate to form an interconnected network of these polymer structures. And this would, of course, be three-dimensional, but we're showing it as two. Okay, so we now have a gel. Typically, these carbon aerogels would then be dried by a supercritical CO2, which will now make a polymer aerogel. So again, with this great big long polymer chain, but if what we want is a carbon aerogel, what then happens is that the sample is calcined to cause reactions to change this essentially into just a carbon structure, as opposed to this long, I'm going to go back a slide. This is clearly a hydrocarbon-based structure. There's lots of hydrogens. We have lots of oxygen groups here, some ether linkages, hydroxyl or alcohol linkages, right? This looks like a great big long polymer chain with a lot of alcohol groups off of it. So the heat treatment in this case is to yield carbon, right? Essentially, they're baking this until they drive off volatile species and cause some oxidation reduction reactions to be left with carbon. And so now this is a form of carbon that's very low density and could have interesting uses. This is not something that you'd use for a window, for example. So, all right, they're going to be highly insulating. And so what we've essentially done in this case is you've added an additional step to make this carbon aerogel, right? At this point, if we stopped in the previous case, we'd have a resorcinol formaldehyde polymer aerogel. But if what you want is just a carbon aerogel, then you're going to have to do this. And so typically this is heating at very high temperatures for a significant amount of time in an inert atmosphere because we're trying to get rid of the oxygen-containing species. If we were doing this in an atmosphere that involved oxygen, that's not going to happen. And so ending up with a carbon aerogel. The previous steps are all the same sorts of steps. The chemistry is different because we're doing the carbon-based chemistry instead, but the whole principle of first forming a sol and then the gel and then doing some aging and making the aerogel is still the same general approach. And you can make carbon-based aerogels out of a lot of different things. You can make carbon-based aerogels out of other synthetic polymers. Some work at NASA used polyimides, so this is one type of organic polymer, to make aerogels that were both strong and fairly flexible. Again, opaque, but strong and fairly flexible. NASA, of course, is a US government laboratory, but they actually licensed the patents that they had on this, and there are commercial products based on NASA's science that are now available, flexible polymer sheets. You can use synthetic polymers like polyimides, but you can also use other natural product polymers. And some of these involve things like lignin and cellulose. And I realize that we're in a building where people are doing a fair amount of work with biomass. And so you can make some interesting aerogel materials using those. You can also use carbon nanotubes or graphene. And on the first day of class this week, Professor Anderson showed a previous Guinness World Record for the lightest or least dense solid. But several years ago, a graphene-based aerogel, and graphene, as I think you've probably heard of, was a Nobel Prize a few years ago for graphene. Graphene is a single layer of graphite So it's a one long molecule, has very unusual properties. Graphene aerogel made by a group from China currently holds the Guinness World Record for least dense solid. You are reading the units right. This is 0.16 milligram per centimeter cubed. So extraordinarily light, and they're showing it, you know, on top of this little grain, and it's just not even denting that. So it's extremely light material. And so for the last full example that I'll show today, I'm going to show, and unfortunately I couldn't get this to be not blurry, a lignin-based aerogel approach. So starting with some lignin, from which there are many waste sources from which one could get lignin, from wheat and wood and things like that. The approach that they take is a reasonably high temperature under pressure with water, making a powder, and then this moiety, you should see, does this look like the epoxides we were looking at before? To link things together, and so they use base along with an epoxide. The brackets here is that this is a long polymer chain. So we're taking this material that contains biopolymers, and we're doing enough chemistry that causes reactive groups so that we can get a gel, and then supercritical CO2 drying to yield an aerogel made from lignin. And so there's a lot of work I mentioned earlier going on in natural product-based aerogels. And one of the things that is really important is that you can use things that were waste products from industrial processes, from agricultural processes, and get interesting materials for additional use from them. I know because of the conference, not everyone could be with us today, but I will also talk about a cellulose-based example, and then I'm going to give you a reference to a very nice review article that really summarizes some of the biomass-based aerogel work that's been done. Okay, so here's an example of cellulose-based carbon aerogels, in this case for a supercapacitor application. And so we're starting out with some species, and this is, you know, this is a polymer. So they're showing this squiggle to show that we've got some sort of cellulose thing. They cross-link these together to make hydrogels. And hydrogels are, it's just another term for wet gel. Okay. So we have a wet gel here. The process here is a little bit different in that it's not necessarily a full sol gel process, but you are still making a wet gel. Right? Depending on the size of these polymers, you could consider the solution to be a colloid. You could consider it to be a soluble solution. There can be a little debate there. This was a freeze drying application. They were not so concerned about monolithicity. And so freeze dried to yield aerogels. Pyrolysis is another term for heat treatment. This is sort of heat treatment / burning. So to the kinds of reactions that are happening to give our carbon aerogel. So we're pyrolyzing it to yield the carbon aerogel. In the previous case, they called it carbonization. Okay. So pyrolyzing to yield carbon aerogels, activating with potassium hydroxide to get activated carbon aerogels. And one can purchase activated carbon for a number of applications. This is an activated carbon aerogel, so it just has a much lower density, much higher surface area, and they're using it for adsorbents and things like that. You'll notice that in the reaction, they used some aluminum salt to help with the cross-linking. And down here, it's just the key. We've got the aluminum ions, and then the cellulose, the particular cellulose that was used in this particular case. But in this case, note that you cannot use high temperature extraction. And Professor Anderson and I have spoken with some people doing cellulose work, that because of the time involved, we're interested in trying it with our method. But as soon as they heard what temperature we have to operate at, they said that's not going to work. The cellulose is going to decompose, so we're not going to be able to do that. So clearly, you can use supercritical CO2, but this is also, this example I'm showing specifically because they used a freeze drying approach to this. The article to which I was referring that I think will be of possible interest to a number of people is here. We will be sharing the slides as well as the video after the class, but there's a very nice review that includes very nice tables showing a number of different ways that people have made aerogels using cellulose, using lignin, using various biomass and industrial wastes as resource materials for aerogel preparation. I would encourage you, if this is a topic of continued interest, to take a look at that article. And at this point, I'd like to know if anybody has any questions, because I'm at the end of my slides, I believe. So I appreciate you spending time today, especially with the conference going on here on campus. Does anyone have any questions? And I should also say, although I'm happy to field questions by email, I am just in Perugia for this week, and I'll be back in Schenectady, New York next week, back to my regular teaching schedule there. Professor Ann Anderson will continue with the lectures in this series next Wednesday. And she will be in Perugia for the essentially the entire month of April. Does anybody have any questions? Okay, if not, I'm going to let you go a few minutes early. Enjoy the rest of your day and the rest of the conference. It's been a pleasure to interact with you here at Perugia.